primarily the method of undetermined coefficients and the method of variation of parameters with a single example so you can kind of compare the two and also understand when or why we might choose one over the other method. Okay, so in both cases, you start out the same. The goal is to solve the homogeneous situation of this differential equation, which amounts to setting the particular uh, function this equal to 0. So for the homogeneous, we have this situation, and we're going to solve this differential equation. Since this differential equation is linear second order with constant coefficients, we're going to not lie, let y equal e to the rx. Differentiating twice, we get the characteristic equation r squared minus r minus 6 equals 0. Solving for r, this is an easily factorable. So we can show that this is r minus 3, r plus 2 equals 0. And so the roots of our characteristic equation are r equals positive 3 and r equals negative 2, which then allows us to write the solution to the homogeneous differential equation yc as a c1e to the 3x plus c2e to the negative 2x. Okay. So we're going to first, now that we have this differential equation, the solution to the homogeneous part, we're going to look at the particular solution, which is 2 sine of 3x, and we're going to utilize the fact that since we know this, this is a 2 sine 3x. This is of the form for a particular solution guess of yp equals a cosine 3x plus b sine 3x for the undetermined coefficients. Ooh, it helps if you can spell and speak properly. Undetermined coefficients method. And we're going to do this one first, and you'll see why in a second. And the reason why we're choosing this combination is because our particular solution could have possible linear combinations of both sines and cosines. And so if we only choose to let the particular solution be a value of sine, we may be missing out on part of the particular solution. Okay, so we need actually both to make sure that we're catching all possible solutions. All right, so now that we have yp, we're going to take the first derivative, and that's going to give me 3 negative, I forgot my 3, and my negative sine 3x plus 3b cosine 3x. And then my particular solution, the second derivative, is going to give me negative 9a cosine 3x minus 9b cosine 3x. Okay. All right. So there are our 3 functions that we're going to place back into the original equation, and then we will set it equal to this. This is where we're going to evaluate our undetermined coefficients. So plugging these 3 back in, we have negative 9a sine 3, nope, sorry, I'm looking at the wrong way. Negative 9a cosine 3x minus 9b sine 3x. Okay, that's y double prime minus y prime, which is negative 3a sine 3x plus 3, I forgot my 3b cosine 3x, and then minus 6, and y was a cosine 3x plus b sine 3x. And that is all equal to 2 sine of 3x. Okay? All right. So now, for me, I think that what's most useful is to gather all the cosine terms together and all of the sine terms together. So I'm going to factor out that common factor of cosine over here. So I'm going to have cosine of 3x. And then looking at this is going to be a negative 9a from here. I have a 3b, but it's a minus 3b, so minus 3b. Minus going from distributing that negative in, or the minus sign. And then here I have a minus a positive 6a, so this is minus 6a. Okay, So that's for the cosine, and then adding to that, I have the sine term of 3x, and I have a minus 9b here. So here I have a positive 3a, negative and a negative make it a positive, and then a minus 6b here times the sine is equal to 2 sine 3x. And the reason why I like doing this now is you can see the sine term and the sine 3x, well, that means that this has to equal 2, and that the coefficient needs to equal 0 since there's no cosine term on this side. All right, so doing that then, and recognizing that these can combine to like terms, I have a system of equations, negative 15a minus 3b equals 0, and negative 15b plus 3a equals 0. Okay, so if you can solve this in any number of ways, substitution, elimination, you could use the Jacobian, however you choose to do so. You're going to find that a is equal to 1 over 39, and b is equal to negative 5 over 39. And I solved it by solving this for b, or for a, actually, and then plugging that in. That's the b, that looks weird. Plugging that in here and solving for a, and then plugging back in here to get for b. So this is my coefficients then, and as you can see, we actually do have a mix of cosine and sine. So this is an example where if we hadn't have chosen this particular solution, we would have missed out on the values of cosine for our function. Okay, so putting all this together then, our yp is going to equal 1 over 39 cosine 3x minus 5 over 39 sine of 3x. And so our general solution is going to be yc plus yp. So here's yp. And so our general solution, which you can clearly read from my very legible handwriting, is y equals yc plus yp, which is c1e to the 3x plus c2e to the negative 2x plus 1 over 39 cosine 3x minus 5 over 39 sine 3x. Okay? All right. So the most difficult part of using undetermined coefficients is making sure that you have the correct form for the particular solution that you're trying to guess. Okay? All right. So now we're going to utilize the method of variation of parameters to solve the exact same problem and just kind of show or contrast the two methods. All right, to do that, we already know that our y1 is going to equal e to the 3x, and y2 is going to equal e to the negative 2x. Okay, that's what we found from up here in our particular solution, or not a particular solution, I'm sorry, our homogeneous solution. And so we have the constraints that we've imposed by the variation of methods parameters. We have y1 u1 prime plus y2 u2 prime. That term has to equal 0, and then we also have that y1 prime u1 prime plus u2 prime, sorry, y2 prime u2 prime has to equal whatever our function is divided by the coefficient of the original. Since a for our differential equation, a is the term from here. Since that's 1, it's just f of x, which for us is the 2 sine 3x. Okay. We know what y1 and y2 are, so we just got to plug those in. So I'm going to work on the first equation here and solve it for u1 prime, and then I'll plug that into this equation and see what we can get out of that. So y1 is e to the 3x u1 prime plus u2, y2 is e to the negative 2x u2 prime, and that equals 0. So that tells me then if I subtract this term over and divide by that, this term is going to become u1 prime equals negative e to the negative 2x minus 3x. If you're wondering where that comes, I'm multiplying by e to the negative 3x on both sides. Or think about it as dividing by e to the 3x. And then this is going to be u2. Okay. So simplifying just a little bit more, u1 prime equals negative e to the negative 5x u2 prime. Okay. All right, so now that we have u1 prime in terms of u2 prime, going back up here, that's really nice because that allows me to simplify, taking the derivative of y1 prime. So I'm plugging into y1 prime, u1 prime plus u2 prime. Sorry, let's see u2 when I say writing y2 prime u2 prime equals 2 sine of 3x. So I'm utilizing that second equation here. And now that I have u1 prime in terms of u2 prime, that will simplify this. Okay, so let's plug that in. So the derivative of u1 is going to be, or y1, sorry, I keep saying the wrong thing. This is 3 e to the 3x. That's the derivative of y1. u1 prime, well, u1 prime was, what is it? It's negative e to the negative 5x times u2 prime. So this is y1 prime. This is u1 prime in terms of u2 prime. Plus, I have e to the negative, oh no, sorry, I need to take the derivative of y2. Well, that's going to be a minus 2e to the negative 2x. That's y2 prime. And then u2 prime is equal to 2 sine of 3x. Okay. All right. So this is y1 prime. This is u1 prime in terms of u2 prime. And then this is y2 prime, and this is u2 prime. Okay. Now, if I multiply e to the 3x times e to the negative 5x, the minus sign will come out. You're left with the minus 3 e to the negative 2x. Adding exponents when you have a like basis. 3x plus a negative 5x is the minus 2x. That's a u2 prime, so I'm factoring that out. Minus 2 e to the negative 2x is u2 prime. I factored out the common form of u2 prime equals 2 sine of 3x. And so notice that these are like terms, so I can put them together. This is going to be a negative 5. And so I have u2 prime is equal to negative 1/5, the 5 coming from here. When I divide by e to the negative 2x, the negative exponent comes upstairs, and this becomes e to the positive 2x. And then I'm multiplying that by 2 sine of 3x. So the 2 I'm going to put with the fraction here. And so I have e to the 2x times sine of 3x. And so now that I have all of that together, I can simply integrate both sides, put a dx here. And so I get u2 is integrating this. I would use integration by parts twice. And doing that, I did the integral actually in Maxima, but if I was going to actually integrate this, it's just it's the multiplication or the integration by parts twice. You'll recover the sine of 2x term, and then you add that term over. Once you're done with that, then you get u2. And so u2 for us is going to be, what it have to be, is equals e to the 2x over 65 times 6 cosine 3x minus 4 sine of 3x. Okay, so that's the result for u2. Now finding u1. Okay, so finding u1 then is equal to, remember from up here, u1 prime is the integral of u1 prime, which is equal to the integral of negative e to negative 5x times the derivative of u2. Well, I'm running out of room, so I'll put that in here, dx. So this is a little bit of a nice exercise in both differentiation, multiplication, and integration. So you would need to take the derivative of this term. and then multiply it by e to the negative 5x. And when you do that, you get an expression, which then you can integrate by parts. The result of which gives me u1, which I found to be e to the negative minus 3x over 15 cosine 3x plus sine of 3x. So this part here, uh, the arithmetic, the integration part of it is a little bit long, um, because of the fact that you have the product of two transcendental functions, because you're also taking a derivative of a product rule, and then multiplying that by another product, and then integrating that by parts. And since it's the integration of two transcendental functions, integration by parts, you're going to have to do it a couple times, just like you did up here, uh, and then add and subtract the terms over to get the closed form of the integrals. So it is a little bit involved for the sake of time. Just showing you the result here, but that's what you would do. Okay, and now that I have that all figured out, I have u1 and I have u2. And so remember, our particular solution, yp, is of the form u1 y1 plus u2 y2. Okay, and so that is actually pretty nice because we know what each of these are. So here's u1, and y1 and y2 are up here. So if we just plug those in, this is what, negative e to the negative 3x over 15. Then we have cosine 3x plus sine 3x. I was surprised that you get two positives there. I mean, it's all negative, but the negative gets factored out. I was assuming that there would be mixed signs when I was actually doing it. And then times, this is going to be times y1, which was e to the 3x, plus u2, which was e to the 2x over 65, 6 times cosine 3x minus 4 times sine 3x times times y2, which was e to the minus 2x. Okay, and so what you should notice is that here the two exponential terms drop out. Multiplying like bases, add the exponents, you get e to the 0. And so this literally just becomes distributing through, we get 1/15. That's a 15. Cosine 3x plus 1, actually it's minus 1/15. Sine 3x plus 6 over 65 cosine 3x minus 4 over 65 sine 3x. Okay, and so once you have that, then just note you're combining like terms. So if you add those two together and you add those two together, once you add those two together like so, you actually end up recreating the exact same value we got here for the particular solution using the variation or using the coefficient, undetermined coefficients. So we get the exact same results using either the undetermined coefficients or the variation of parameters. In this particular case, you can see that the variation of parameters method, while it gets us there, includes some pretty challenging or pretty difficult integrations and requires quite a few more steps. So if we can use the method of variation or the method of undetermined coefficients, it typically is a little bit more efficient at getting to a solution. The problem is that the particular solution has to be of a certain type, and this method always doesn't work, or doesn't always work, I should say, in the same way that uh, this method will always give us a solution, but it may give us a solution that we can't integrate, or the integrals can be difficult. So this one will always work. This one, you need to have a particular solution of a certain type. The one way to make sense of this, if it helps, is that this method is kind of like solving, like up here, right? When we solve the characteristic equation, solving the characteristic equation this way with factoring is like undetermined coefficients. It works in this case, and it's much more efficient than using the quadratic formula. But the quadratic formula would have given us the exact same results. The quadratic formula, is much like the variation of parameters. It's a much more general method, and it'll work every time, but sometimes it just requires a lot more mechanical work. And so the other method sometimes saves us time or multiple steps or uh, reduces the chances that we'll make an error in our arithmetic along the way. Okay. I hope that that comparison example was helpful, and thank you for your time, and I hope I'll see you in the next video.